Hi friends, let's look at problem 1466 and problem 2858. These two problems can be solved using same idea. In this video, we are going to do problem 1466 and also as a preparation for problem 2858. So the latter problem is a little bit harder. So in this video, we are going to solve this problem using traversal. Here actually we can use breadth first traversal, and also because of the problem setting we can also do DFS, depth first traversal, and we can do iterative format. Also we can do recursion. So first let's look at the main requirement for this problem. So here we are given n cities, and also we are given a list of directed edges. So we want to find the minimum number of edges changed so that we can arrive at city 0 from all the other nodes. So here are some examples. Let's look at example 1. So because we are going to first explain the solution based on breadth first traversal. So we are going to use breadth first traversal to digest this example. So here we are starting from source 0, right? So then we printed the graph is bidirectional. Then we go to layer by layer. So then from 0 we can look at 1 and 4. Because 4 is pointing towards 0, we don't need to change direction. And 1 is not pointing to 0, we need to change direction. So here is a count by 1, right? So this current layer is 1, 4. So then we go to next layer. So it's 3 and 5, right? So here 3 is not pointing towards the direction of 0, so we increment the count by 1. And the 4 is also not pointing, 5, this edge also not pointing towards 0, so we are also going to do increment. So we are going to do increment 2, right? So then we go to next layer, that is 2, right? Because 2 and 3, the edge is pointing towards 3, towards the direction of 0, so we don't need to do count increments. So overall we get 3, so if you add them together. So that's also the logic we are going to first code. So with that said, I guess you have some understanding about the problem. So we are going to explain the details when we do the coding. So first we are going to do a iterative format of solution to digest the problem logic. So we're going to have a graph, so collections, default dict. So we're going to use set as the default container, right? So also I want to maintain a set which contains the directed edges. So because we are going to traverse these connections, so we can add the direct edges one by one to the edges set, or you can do, say, let's say you can do this. So tuple atom for atom in connections. This is also good. So here for start and end in connections. So which means that there's a direct edge starting from S pointing towards E. Because we want to so this is the current edge. Because we pretend graph is bidirectional, so we also want to do this, E at S. And in this loop, so also we can update the edges. So here we need to add a tuple. So here we only consider directed edges. So this is for convenience of membership check, because here we're using set. So this is the one part, build graph. So next we are going to do traversal. So first I'm going to do a traversal, breadth first traversal. So let's initialize a result variable. So this is the counting variable. So we are going to return its final state. That's the minimum edges changed, right? So here we can use BFS. So from a source, you can think of the source as city 0. So because we want to modify this result variable using this function, so we're going to non-local it, right? So this is the one way to treat this change, because here result is immutable. And another way to treat this is using a class attribute, right? So then what we are going to do, first we are going to make a set. So this is to avoid repetition, right? Then we can have a queue collections deck. So we can add the source to the queue. And then we are going to do the standard traversal. But in the process of traversal, we want to count the number of edges we need to change direction. So basically, well, queue. So we get this node is queue pop left, right? And then if node not in visited, so we're going to visited add this node. There's nothing to explain, right? Because this means that we have already visited this current node. We don't want to come back again. Then we check the neighbor for neighbor in graph node. So if neighbor not in visited, then we consider it, right? So then we want to look at the direction. So if we are going to have from node pointing to neighbor, so this is reading the offset, right? So we need to increment the result variable, right? So we can do a check. So let's see if node neighbor in edges, because edges is a set, so this check is O1 operation. So if this is the case, we are going to increment that. Otherwise, we don't increment the result. And then we can include this neighbor. So that's the overall role of this function, BFS. Then if we call this BFS from the city 0, then we will get the result. So we just need to return it. So let's do a quick check. Right? It passes one example. Now let's look at the generic case. It passes all the cases. So before we make some comments, let's first make one, right? So this is in this problem for problem 1466. So starting from source, any node. So basically you can get the minimal number of direction change, right? So that we can reach source from all other nodes, right? So if we connect this one with problem 2858, so what we want to compute in this problem is the minimum number of direct changes so that we can reach all the other nodes from the source. This actually is essentially the same, but the problem for 2858 is more difficult besides this difference. So this is the one point. Another point is that, so here we are using deck, but we are append from the tail and pop from the head. If we just use pop, so here essentially we are using this queue as a stack, then this corresponds to DFS. Let's check that. Yeah, it passes. So let me change back to BFS. So this version is an iterative format. Hopefully you have a better understanding of the problem logic. So now I want to write a recursion solution. So we are going to use DFS. So I'm going to change this one to be version v1. So here does not change. So we want to change this part. So I can use this is a set to avoid repetition. Then I define DFS. So from source. So also we want to modify this result variable. So non-local is the result. And then what we want to do is that if source not in visited, so we first add this to visited, meaning that we don't want to come back. Then we are going to check the neighbor for neighbor in graph source. So if neighbor not in visited, essentially the same code as above, but so then we want to check direction, right? If source to neighbor, in edges. This means that we want to change direction, so the count is incremented by 1. So otherwise, we just need to do traversal starting from the neighbor. So we want to do DFS neighbor. That's the function. Then if you call DFS 0, so you are going to get the result. Let's do a test. Yeah, it passes 1. Now let's look at the generic case. Yeah, this is the generic case. I guess up to now, so we finished the coding for the current problem 1466. So next we're going to move to problem 2858 in a follow-up video. Thank you.